In topic 3, we started talking about alcohols and ethers. Um, Covered a variety of topics. We mentioned alcohols, physical properties relative to things like ethers or hydrocarbons. These are primarily derived from the polarity of alcohols combined with their hydrogen bonding. We learned a number of ways, and this is more of a review from earlier sections on how to make alcohols from double bonds or olefins. These are hydration under acidic conditions, oxymercuration, demercuration, hydroboration, oxidation reactions. We talked about the things that went into the relative acidity of alcohols. And some of the reactions that we use really consistently for the rest of the course are converting alcohols to halides to make them leaving groups. These include methods such as going through carbocations with strong mineral acids if they're primary, secondary, or tertiary. Or if it's primary, these will go through an SN2 process. And this affects the relative rates of substitution as well as the overall stereochemistry and potential for carbocation rearrangements. Some of the more useful reactions that we ended up using and learning about were things like the phosphorus halides that'll turn an alcohol into, say, a bromide with PBr3, or thionyl chloride pyridine to turn it into a chloride, and also using sulfonate esters, and our primary reagent here is tosyl chloride. This will allow you to turn an alcohol into a good leaving group without interrupting its stereochemistry. Other ways that we learned of using alcohols were in synthesis. This involved things like Williamson ether synthesis, where you could have, say, a leaving group on an R group, and you're going to deprotonate an alcohol to make it an alkoxide, and it can do an SN2 attack. This lets you make unsymmetrical ethers pretty well, though you still have to worry about E2 elimination for more substituted cases. And also that we can do alkoxymercuration demercuration if you run the reaction in a solvent like ethanol or methanol rather than in water. There were times where alcohols got in the way, so we needed to put a protecting group on it and then take it off afterwards when we want to do intermediate reactions. Putting on the silyl ether TBS was more useful overall than tert-butyl group. There's not many times where you need to use a tert-butyl group where you can't use the TBS. And you could put these on using TBS chloride and imidazole. Imidazole was our base for this reaction. And then we had cleavage of ethers with strong acid, which strongly mimics the conversion of alcohols to halides. It's just now you have a different molecule leaving. You have a whole alcohol leaving that could potentially further react with these strong acids to make more alkyl halides. Epoxides were very useful molecules. We learned how we can make them from double bonds with MCPBA. So if we have a double bond treated with MCPBA, and this will give us an epoxide. And we learned how if we have acidic conditions, we're going to be protonating the epoxide, and we're going to have a neutral nucleophile ring opening at the more substituted carbon, or the carbon that is better at stabilizing positive charge. Whereas if we try to ring open this under basic conditions, where we have something like an alkoxide, it will just attack the carbon that is least sterically hindered. So you have two different ways to ring open epoxides, whether you're in acidic or basic conditions. And along the way, we also talked about acidity of phenols in this topic. So to just kind of reinforce some of the elements, both of elimination chemistry and also substitution chemistry all at once. This is a question that we had. It was either on an exam or a problem set. And the first step is the reaction of PBr3 with this alcohol. So we can draw this same alcohol. And PBr3 is an electrophilic reagent. So the alcohol ends up being our nucleophile. Phosphorus is tetrahedral, so we can do a direct SN2 attack on the phosphorus to kick out the bromide. This ends up being a favorable process that's really accelerated by making a strong phosphorus-oxygen bond as well. The hydrogen is still attached to this oxygen, so it's positively charged, which means it's also going to be a very good leaving group. The counter ion we have is a bromide anion, so it'll be the nucleophile that's able to come back and attack this carbon in an SN2 fashion, thereby inverting the stereochemistry, and we end up with a bromide that is down. In the second step, we have potassium tert-butoxide. This is a very strong base. It's not very nucleophilic because of the big tert-butyl. And so a lot of times that'll tell us where a deprotonation will take place in an E2 elimination. This molecule is actually a little bit different in that it's in a rigid six-membered ring. So we actually have chair conformations. So you know that in an E2 elimination, we need to have an anti-periplanar relationship of the hydrogen and the leaving group. So we can draw this structure in a chair form, and it gives us information about how this molecule can actually eliminate. So since we have this bromide bond here, we need a hydrogen that's going to be anti-periplanar. And there's only one hydrogen that meets that criteria. On the other side, the anti-periplanar bond is a methyl, and you can't have a methyl leave in an E2 elimination. So this means our tert-butoxide really only has one choice. It'll be able to grab this carbon, kick out this bromide, and this allows us to choose the answer C, where the double bond is going towards that ethyl group. So we learned other ways to invert alcohol. So what if we used HBr instead? How would things change? So HBr, the first thing that's going to happen is the alcohol will be protonated by HBr. I'm just going to have this equilibrium arrow going through the answers. And we're on a secondary carbon. So that means that the faster process of a protonated alcohol will be fragmentation to make a carbocation. With carbocations, they don't really have much preference. This means we could really go and take a proton from either side. If you imagine having the bromide come back and take this hydrogen, we're going to be left with this olefin isomer. Whereas if it takes this other hydrogen, we'll make a different isomer. Under these types of conditions, we would expect the more stable double bond to form. And there's not a really big difference between either of these two double bonds. Both are tri-substituted. The substituent effect of an ethyl versus a methyl is going to be pretty much the same. So we would say we'd make a bit of both. So generally I'll be designing questions so that there's going to be one predominant answer. But just to help try to compare and contrast the two different modes and remind you guys of some of the reactivity of these two different methods for turning an alcohol into a bromide. Now we have this is going to be a bit of review from Organic 1, but it never hurts to go back and think about it some more. This is a hydroboration oxidation question, but we're using deuterated borane, so it lets us follow where this hydrogen goes a bit more closely. And this will help us to reinforce some of the stereochemical elements of the hydroboration oxidation reaction. So the first step is the addition of borane across the double bond. So this is a concerted process where you end up transferring, oops, I automatically drew hydrogens, the deuterium to the double bond at the same time that the boron makes a carbon-boron bond. So this is overall an electrophilic molecule. Borane has an empty p orbital. So we can imagine this carbon-carbon double bond attacking the boron. This will start to generate positive charge on this carbon. So we know where the boron goes because it will result in positive charge on the more stable carbocation. But before that carbocation even fully develops, the hydride, or in this case deuteride, attacks back and makes a carbon-hydrogen or carbon-deuterium bond. So we see our initial stereochemical result is having the boron and the deuterium on the exact same side of the molecule. So we have a methyl group up, we have the boron and deuterium down. It's a syn addition. Potentially these other two boron-deuterium bonds can do other hydroboration oxidation reactions, but just for simplicity, we'll just draw the hypothetical oxidation from here. So when we add in the peroxide anion, we have this very nucleophilic peroxide. It'll attack the empty p orbital of this borane. We still have our methyl up, our deuterium down, and our boron down. Only now we're going to have a charge form on boron. I'm just going to say R because this could be either thing. This wedge doesn't look very clear, does it? We have a formal negative charge on the boron. And this is where the weird 1-2 shift takes place. So this boron has nucleophilic bonds now. This oxygen-oxygen bond ends up being very weak, which makes this oxygen a good leaving group. So we're going to have the arrow, the carbon-boron bond, actually attack this oxygen, kicking out hydroxide along the way. This does not change the stereochemistry. Stereochemistry keeps the exact same orientation. But now we can see how this answer will finish up. Along the way, the borate ester gets hydrolyzed. The methyl is up, deuterium's down, and the oxygen is down. So now we can see this is most consistent. We have a variety of options available to us. We know that A is impossible because we didn't even put an oxygen on it. C and E are not possible because these are not syn additions. And between B and D, B ends up being the one that puts the deuterium in the right place, that gets the right anti-Markovnikov hydration of the double bond overall. So now we have an epoxide question from from I believe the second exam. There's a couple things to notice. We have basic conditions, sodium hydride and butanol. This means we're going to have the butoxide anion form. We're under basic conditions. So we know this butoxide anion is going to attack the epoxide in the least substituted position. So one other thing to note, though, is that this stereocenter stays up in both cases, but now first it was leaning to the left and now it's leaning to the right. This tells us something else must happen in this reaction. So epoxide ring opening is very fast relative to a potential SN2 reaction that is very slow. So we're going to be able to have this butoxide make an intermediate alkoxide. And now we have this chloride available as a leaving group for the alkoxide anion. So this will allow us to make now a new epoxide at the end of the day. So this is tempting to just draw an SN2 and try to get you to the correct product, but if you keep track of the stereochemistry, you note that the epoxide ring had to ring open and this O- needed to attack. Now this last cyclization, even though it's making a strained three-membered ring as fast, just because three-membered rings are formed quickly because the atoms are so close to each other. Topic 4, this will be the last topic we'll cover in this video. This had to do with aldehydes and ketones, largely looking at their reactions as electrophiles. We had them reacting with a large number of different types of nucleophiles. We found different ways to make carbonyl aldehydes and ketones from alcohols, and then of course the addition reactions with, say, our reducing agents like sodium borohydride, lithium aluminum hydride, and diol. We talked about making hydrates, hemiacetals, and acetals. These all had very similar mechanisms. You can make hydrates and hemiacetals under basic or acidic conditions, but acetals are only under acidic conditions. We learned how imines and enamines can be formed with acid catalysis whenever you have a ketone and an amine combined. Using that, we were able to make hydrozones to use the Wolff-Kishner reaction for a new way to remove carbonyl compounds to CH2s. And we also learned a carbon-based nucleophile to add into ketones and aldehydes, which is HCN, which is frequently accompanied by just cyanide a bit. That'll add into ketones or aldehydes to give you what are called cyanohydrins. These are surprisingly stable. These are much more stable than a normal hemiacetal would be. Perhaps an outlier, one of the weird reactions we learned is the Baeyer-Villiger, and this is when you use some sort of peracid. Frequently this is MCPBA, so it's more than just epoxidizing double bonds, to insert an oxygen between a carbonyl and the neighboring carbon of a ketone and turn it into an ester. We learned that the group that migrates is generally the one that is more substituted. It's because it's better at stabilizing positive charge. We learned a variety of other types of nucleophiles that can go and add into these carbonyl compounds. These include organometal reagents, where they had a variety of reactivities, which I will discuss in a minute. We learned how to make them. We learned what types of carbonyl compounds, the selectivity employed. These also are able to ring open epoxides. Of course, these are under basic conditions, so you would expect to attack the less substituted position. And also keeping in mind the compatibility of these with a lot of other functional groups, since they are frequently very, very basic. And at the end of this topic, we learned new ways to make double bonds with Wittig and Horner-Wadsworth-Emmons reactions. The Arbuzov reaction kind of went with the HWE as a way to make the phosphonate esters. And in both cases, the general idea is that you end up with some sort of phosphorus ylide or ylide-like molecule that was able to react with, say, an aldehyde or ketone. To do this 2+2 type reaction, that'll give you a oxaphosphatane, these three-membered or four-membered ring intermediates that will go to make more carbon or for oxygen, more phosphorus oxygen bonds, thereby giving you a double bond and the phosphine oxide. So making and breaking acetals was something people had quite a bit of trouble with, I think, in this section. So I just want to talk about one more time one of the examples from the exam. So in this case, we know that we have two different types of acetals. Just as a reminder, acetals have the general form where we have two ethers attached to the same carbon, central carbon. I'm going to call this the acetal carbon. And so the first part of these reactions is to identify what is the acetal carbon. We see we have two different acetal carbons. And when we hydrolyze an acetal, we end up making the carbonyl from where that carbon used to be, and you'd end up making two equivalents of the alcohol. So in this case, we can follow the same sort of logic where we're going to take this central carbon and we're going to go and turn it into the corresponding carbonyls. Note that if this acetal carbon had one carbon and one hydrogen, we would end up making an aldehyde instead of a ketone. And in this case, each of these do have hydrogens. So to draw the main product, we just need to be able to identify where that acetal carbon is, turn it into the correct carbonyl, and along the way, we would end up making or having two molecules of methanol leave, since those are the two substituents. This is a fairly strange instance where we have a cyclic acetal where one of the oxygens is shared by both. And so in this case, we just end up kicking out the two R groups on the sides. Similarly, going the reverse direction, we can go this way if we have acid, and usually we'll have this being tosic acid, so it can be done in a non-aqueous environment like toluene to help remove water. And in the same way, we want to identify what is our alcohol. Frequently, we were using diol molecules to help us make 5-membered ring acetals. And if we recognize where this carbonyl is, we just need to now attach both of these alcohol groups to that central carbon to make the acetal afterwards. The next one is a reduction reaction. So we have a few different steps because we have an oxidation, a reduction reaction with diol followed by an oxidation. So diol is one of these weird reagents. I'll draw it out to the side. So diol is a Lewis acidic reducing agent. Because it has this MTP orbital on it, that means it'll accept electrons from the oxygen first, and then afterwards it'll be able to reduce the carbonyl. Remember that diol is able to also reduce esters selectively to aldehydes, and this is because the tetrahedral intermediate that forms is stabilized enough so that it can't collapse. So it's not that diol can't reduce an aldehyde, it's that an aldehyde does not form during the reaction when diol is added to an ester. So with that knowledge, we have excess diol. That means we'll be able to reduce the ketone to a secondary alcohol, and this methyl ester will get reduced to an aldehyde. So after workup, so I'm going to say after 2, we're going to have this product. We're going to have an aldehyde and a secondary alcohol. Next we have silver oxide. Silver oxide has one job. It only does one thing. It oxidizes aldehydes to carboxylic acids. It will not oxidize alcohols. They'll keep them in the same oxidation state. So this is a very mild selective way to make carboxylic acids from aldehydes. So the main reminder is that diol can reduce aldehydes and ketones. It's just that an aldehyde does not form during the reduction of an ester like it would with something like lithium aluminum hydride. Now we're getting into the topic of which reagent is most basic. And this has to do with the nature of different carbon-metal bonds. So the more ionic a carbon-metal bond is, the more basic the carbon will be. That'll make it behave much more like a carbanion. So usually this involves counterions that are going to be on the far left side of the periodic table. So things like lithium and sodium will end up giving you very ionic bonds. So these will end up being the most basic. When you go all the way to even somewhere to like zinc, these start to make more covalent interactions with the neighboring carbons. Their bonding is more shared, so it's less polarized. And when you get to something all the way to a cuprate, these are really the least basic by far, and as we've learned, don't even react with things like aldehydes and ketones. So we got it down to A and B. We're trying to decide what would be more basic, phenolithium or methyllithium. So keeping in mind that each of these are really a lot like an aryl anion or a methyl anion, we now can go back to some of our acidity considerations to think about which one would be the most basic. So when we think about stability of anions, we want to think, well, are they on different types of atoms? Both are carbons. But within the set of carbons, the two carbons are different. Benzene, it's on an sp2 carbon, whereas on a methyl, it's on an sp3 carbon. sp2 is more electronegative, which means it can be better at stabilizing this negative charge. Since the methyl anion will be less stabilized, it'll be more basic, and we're going to end up choosing methyllithium as our most basic option. Ooh, now we have an addition question. This was from the homework, but since I got quite a few questions about it during class, I figured it probably would be worthwhile to go back and talk about this again. And the key question here, or the key points, are discussing the relative reactivities of an ester versus a ketone. Esters are less reactive than ketones. We can think about the context of, say, a sodium borohydride reduction. Sodium borohydride can reduce ketones, but it can't reduce an ester. This has to do with the extra stability that esters get through this resonance interaction. It's a ground state stabilization, where you have to break up this resonance if you want to make a tetrahedral intermediate, and this is an energetic penalty. The other thing to keep in mind are the relative rates of different steps. So collapse of the tetrahedral intermediate is usually quite fast, faster than an intermolecular addition reaction. So when we have methyl lithium and this methyl benzoate in a 1-to-1 equivalence ratio, this doesn't mean one molecule and one molecule. This means that you have a pile of benzoates and a pile of methyl lithiums, and there's a whole lot of each, but they are in the same molar ratio. So along the way, we're going to have our methyl benzoate. We're going to look at the mechanism. We're going to have our methyl lithium. It's going to attack the carbonyl. We also learned later on that methyl lithium is a hard reagent, so even if there's another option to attack an alpha beta unsaturated, it will definitely attack the carbonyl. This gives us our tetrahedral intermediate. This ends up being a fast step, the intramolecular collapse of the tetrahedral intermediate. And if you imagine, as you're doing these reactions, you start to react these esters, you're still going to have other molecules of methyl lithium in solution because they don't all attack their respective esters at the same time, because this ends up being the slow step. So you're always going to have more methyl lithium around. And when methyl lithium has the option of attacking a ketone versus an ester, it's going to go and attack this ketone every time. So this means that one molecule of methyl benzoate will be attacked twice in succession quickly before all of the methyl benzoate is consumed, because this process requires 2 equivalents of methyl lithium to add in. So if you start with 1 and 1, you'd end up having about half of the original starting methyl benzoate and about half of C afterwards. So we're going to have about equal amounts of C and D. So this is a similar type of question involving diol and aldehydes, but we're adding in one more twist to the end. We have this hydronium workup. So we always have this in diol reactions, and this will help us remember something about acetals as well. So we just discussed how diol reduces esters to aldehydes and aldehydes to primary alcohols. So the first thing to do is just draw out that molecule. That molecule would look like this. And you're probably thinking, if I know my chemistry well, I don't see any of these molecules as an option. So while the workup is able to hydrolyze some of these aluminum salts, something like acetal formation or a cyclic hemiacetal is almost impossible to stop even with just plain water, let alone proper acid catalysis. So this is where we have this alcohol that is 5 atoms away from the neighboring carbon. With a little bit of acid, we're going to end up protonating some of this aldehyde, and this will end up ring closing quite quickly. So after proton transfer, we'd have the option of making this cyclic acetal, so cyclic hemiacetal. So normally hemiacetals are not stable at all, except when we can make a ring with them. The other cases are those very electron deficient aldehydes and ketones that will also have some equilibrium favoring it. So if we think about where this equilibrium lies, it will greatly favor the forward product. And we've seen this type of general cyclic hemiacetal in things like sugars. I think that was the main example we saw in class. So for one more, I think yeah, this is our last example. We have a Wittig reaction. We're just going to go through the mechanism a little bit more slowly than what I showed on that initial slide. The first step almost always involves reaction of triphenylphosphine. It could be another type of phosphine, but usually people use triphenylphosphine because you can't deprotonate any of the phenols. The phosphine is nucleophilic. We can think about this being a lot like a nitrogen in that it can be quaternized with alkyl halides. And this will make a phosphonium salt. So I'm just going to draw a phenyl. It's a positive charge. Now, a consequence of having this positive phenyl next to this phosphonium salt is it'll make the neighboring hydrogens quite acidic, much more acidic than your average CH bond. So when we add in phenyllithium, which is a very strong base, this won't be used as a nucleophile, but it's going to be used as a base. It's going to be able to deprotonate this hydrogen. And you can draw these zwitterionic species in two ways. You can keep it as a minus and a plus. This gives, I think, a good idea of the reactivity because it's nucleophilic at carbon. A lot of organic chemists will write this as a phosphorus carbon double bond. That is just fine as well. In the final step, we're going to add in this methyl ethyl ketone. We'll be able to have the carbon attack. Immediately this oxygen will go to make a bond with phosphorus. Sorry, I crossed over these electron arrows. And we'll get back to making the oxaphosphatane, where we attach the oxygen to the phosphorus. And this phosphorus wants more oxygen bonds, so we'll be able to break up. So the final product we're going to get out is the phenyl. It's going to have a double bond next to it. There's be a hydrogen next to this phenyl. So we have an ethyl on one side and a methyl on the other. So if we go look at our options, we see that this indeed is our best option. Note that the relative EZ geometry, don't worry about it. For this, we won't be able to determine whether E or Z is favored. Sometimes it's hard to predict in some of these Wittig reactions. In the HWE reactions, though, these have much more equilibrium process and will generally give the E isomer. All right, I think that is all for my final review for now. I'll post the acid-base video soon. I'll get some more review on exam 5 to give some more background there. And there's already some, I think, sort of review materials to hopefully help out on YouTube from the exam 4 materials, topics 5 and 6. If you've seen this and you have further questions, I'll be happy to answer them during class on Monday or at the office hours on Wednesday or Thursday night, or if you post something to Piazza.